Hello everybody, welcome back to a new video. This week we're continuing in our module 3 that deals with mechanical and electrical systems. We're on week 7. This week we're going to be talking about electrical systems. The reading for this week is going to be pages 9 through 11 of the ballast reading that I posted to the Blackboard page, and then also chapters 15 through 16 of the course textbook. The notes that I'm going to be giving you here are going to pull from both of those, and then also from some external sources as well. So some of the things that I touch on in these notes may not be specific to either of those readings. So it's important that you read these notes and pay attention to everything that I have put in here. The topic of electrical systems, much like HVAC and plumbing, is very dense, and it would be very difficult to um, touch on all of the concepts of it in depth, all right, because there's just so much involved with it. So just like I did with HVAC, this is going to be more of an overview, sort of a survey of the concepts associated with electrical systems. We don't have to go super in depth with it. We just have to have a basic understanding of how the components that are tied to electrical systems function so that we can make informed decisions and coordinate with engineers and architects who will probably be dealing more with it than we will. All right. So this lecture is going to be a lot of pictures this time around to just give you sort of a good overall understanding of what I'm talking about. It'd be very difficult for me to sit here and try to explain these complex concepts to you just by talking. So I'm going to be doing a lot of pointing things out in diagrams and pictures to help give you a better idea. And also, I have a decent amount of experience with electrical systems. I did some of my own wiring in my house when we were renovating, so I have some experience with how an electrical system works, and what all the terminology is, and how everything goes together. Because I've done some of the hands-on work on my own, so I can kind of speak to it on a personal sort of experience type of level. So, all right, let's get started. So for the introduction, interior designers coordinate with electrical engineers and or electrical contractors to determine electrical system requirements for projects. The interior designer is not directly responsible for the technical specifications of electrical components, but they need to have a good enough understanding of them to schematically show the desired locations of switches and outlets on plan drawings. All right, so you have to be able to understand how these systems function in a simple way, because again, we're going to be coordinating with the experts, and you will be doing some work on your end to determine where the electrical access points, I guess, within the building are. So you're going to have to be indicating those on plans, right? So to start, we're just going to touch on some electrical basics. A lot of this stuff is covered in like science classes. So if you've taken like chemistry classes or physical science classes in the past, you've probably been introduced to these terms, and you've probably learned about them in a greater detail than I'm going to touch on here. I'm just going to give you the basic definitions of these terms so that you can understand them in the broader context of the electrical system as I talk about that later on. All right, so the first term that we have is voltage. Voltage is going to be the amount of potential energy between 2 points on a circuit. Units that measure the amount of electrical, or voltage units are units that measure the amount of electrical potential in the circuit, and they are known as volts. Okay, amperage. This is the process of electricity flowing along a circuit. It's also known as the electrical current. Okay, so when you hear somebody talking about the electrical current, they are referring to the amperage. Amperage units measure or the units that measure amperage are known as amperes or amps for short. And the amount of current or amps needed for a particular purpose determines the size of the wire that is going to be used. Okay, so we're talking about electrical wiring. We're going to be dealing with different sizes or gauges of wiring, and the gauge of wiring that's going to be used for a particular application is going to be directly related to the amperage that is required for whatever you're going to be using the wiring for. All right. Wattage. A watt is equal to 1 ampere flowing under the electromotive force of 1 volt. It is a unit of electrical power that represents the rate at which energy is being used at any given moment. All right. Watts are used to measure how many electrons are passing a point and how much force is available to move them. And electrical power is energy that is used over time. Electrical meters use kilowatt hours to express energy usage over time. All right, so the main point here is when you hear wattage, that's going to be referring to energy usage. So, if you think to your electrical bill that you would be paying for your house, that is going to be calculated using kilowatt hours. Okay, so again, if you hear the term wattage or kilowatts, that's actually talking about the amount of energy, electrical energy, that is being consumed. Okay. All right, now in terms of electrical current, we have two different types. We have alternating current, AC, and we have direct current, DC. So an alternating current is a current that has the level of electron flow changing over time. So the electrons here in this type of current are going to be flowing in two directions. AC currents are the type of currents that we use in building electrical systems. So all of the wiring in our house, those are going to be implementing AC currents into them. Direct currents, this is where the level of electron flow remains constant over time, and the electrons are going to be flowing in a single direction. DC is most commonly used in electronics, okay? But again, just be familiar with the two different types here, and alternating current is the one that we will mostly be focusing on when it comes to electrical systems within buildings, okay? Here's a explanational video if you want to sort of see the difference between the two explained in kind of a more in-depth way. All right, now we're going to actually get into talking about electrical systems within buildings, okay? So starting off here, conductors. Conductors refer to the electrical wires within electrical cabling that is used to carry electricity through a building. All right, so when we talk about electrical wiring, or when people call something an electrical wire, they're probably actually referring to an electrical cable. Okay, so an electrical cable is going to be it's like basically one big wire that has individual wires inside of it. So if you look at this picture down here, the yellow thing that you're seeing, that is the cable, but then within it you can see we have these three individual wires, okay? So it's not like it's just one giant wire. It's actually a cable that's housing individual wires inside of it, and each individual wire has a specific purpose. All right. So there are different types of cabling that can be used in an electrical system, and each of them has their own purpose. Non-metallic, or NM, sheathed cable. This is going to be your most common type that you're going to be seeing. It's also typically referred to as Romex. That's kind of the industry standard name for it. So if you hear somebody saying the word Romex, they're talking about this type of cabling. This is electrical cabling that consists of two or more plastic insulated wires plus a ground wire that is sheathed with a moisture resistant plastic jacket. Okay, and what we're seeing here, this is an example of a 12 gauge Romex cable bundle. So this is if you were to go to like the electrical wiring section of like a home store like Lowe's or Home Depot, you'd probably be seeing bundles very similar to what you're seeing right here. We also have conduit. Okay, so conduit is a tube that is used to protect and route electrical wiring in a building or a structure. It's commonly made of metal or plastic. It can be rigid or flexible, and it's required for fire-resistant construction in commercial structures. So here you can see we have some rigid conduit. So this is conduit that is not bendable. Okay, it's just basically metal pipes, and the wires are contained within there. And then these are meeting up with flexible conduit. So you can see this is actually a metal sleeve that is bendable. Okay, so this can bend and it can move in a bunch of different directions. You might also use conduit in situations where you have to embed it, like into concrete. So if you have concrete panels or a concrete slab that you have to run electrical through, you might embed the conduit within the concrete. All right. So when we're talking about wiring, we have a bunch of different wiring types. Like I said, we have our cable here. That's basically just the bundle of the individual wires together as one unit. But then individually we have the wires themselves within the cable. So these are the different types of wires in electrical cable. First we have our hot wire. This is the wire that carries electrical power from the power source. The power source in our case being the service panel to the receptacle. Usually it's going to be sheathed in black or red plastic, okay? Almost always you're just going to see a single cable, which is just black, but then in some cases where you have multiple, you can have multiple hot wires within an individual cable, and usually you will see a black one and a red one next to each other. Next we have the neutral wire. So a neutral wire is a wire that carries electrical power from the receptacle back to the power source, okay, service panel, to complete the electrical circuit. Usually it's going to be sheathed in a white plastic. All right, so here's our hot wire. Here's our neutral wire right here. And then we have the ground wire, and that's going to carry an unstable electrical current away from the electrical system and send it downward toward the ground. Usually it's going to be bare, but it may also be sheathed in a green plastic. All right, so in a Romex cable, this is what your ground wire is going to look like. It runs between the hot wire and the neutral wire, and it's usually, it's not insulated, meaning it usually doesn't have plastic around it, but it will usually have this brown paper kind of surrounding it. And again, the point of that is to take unstable electrical charges and move them or direct them toward the ground. And that is kind of a safety measure that's implemented into modern cabling, and we're going to talk about that a little bit more in depth later on here. All right, but basically the purpose, when you have an electrical circuit, you have to have a wire that takes the power from the main source, so that's going to be our service panel in a house that's going to be somewhere down in the basement probably, and this hot wire is doing that. So it's taking the electric from the service panel, it's taking it to the receptacle being the outlet or like a light fixture or a switch, okay? And then once it gets to the receptacle, the electric has to have a way back to the power source. So it has to find a way back to the main service panel. Okay, and that's what the neutral wire is for. After the power has been run through the receptacle, it's going to go into the neutral wire and it's going to run all the way back to the power source. All right. The gauge now, this is the thickness of the cable and the wires within it. All right, so American Wire Gauge, AWG, this is the U.S. wire and cable industry standard for round cross-section conductors. So anytime you have a cable that has a round shape like this on its cross-section, that's going to use the AWG standard to reflect the gauge for that wire. So if you were to look at wiring that you buy from the store, it's going to have a rating on it. It's going to be a number that's indicating the gauge for the wire. So it's referring to how thick or how large that wiring is. It could be 10 gauge, it could be 12 gauge, 14 gauge. But that number on there is going to be the AWG number. Okay, and that's just an industry standard for electrical wiring. A lower gauge number is going to indicate a thicker cable, while a higher gauge number is going to indicate a thinner cable. All right, so remember this. If I were to say, or if I were to compare like a 12 gauge wire to a 14 gauge wire, the 12 gauge wire is going to be thicker than the 14 gauge wire, and that might not be what you're expecting. You might be anticipating the one with the higher number to be thicker, but actually it's like inversely relational. Okay, so if it has a lower number, it's going to be a thicker wire, and if it has a higher number, it's going to be thinner. So make sure you remember that. Thicker cables are rated to carry more amps. All right, so we're going to have different applications in our building, different appliances that need different amounts of energy carried to them. All right, so let's say you have an appliance like a stove. Those draw a lot of power, and they need a lot to power them so that they can function properly. So in those cases, you're going to need wiring that has a lower gauge rating, and that wire is going to be thicker so that it can carry more amperage through it. Okay, so it can meet the requirement for that appliance. If more amps are being sent through a cable than the cable is rated for, the cable may overheat and start a fire. So there's going to be different code requirements associated with cabling and the gauge of cabling that you need for a particular application, because if you are trying to draw too much power through a cable that is not rated to deliver that much power, it's going to cause a failure, and that failure is usually going to result in a fire starting because the cable is going to overheat. Okay, so if these cables are bigger, right, they have a larger gauge to them, they can carry more energy safely through them. All right, so here's an example of different gauges of wiring and the typical applications that you'd use them for. So you can see here we have a 3/0 gauge wire. This is not 30. This is a 3/0 gauge wire. And this type of wiring, you can see we have seven. Yeah, we have 7 individual wires bundled together within this cable. Okay, and this is going to be rated to carry 200 amps of electricity, and this is what you would have at the service entrance. So if you think about the wire that's coming into your house from the outside to your electrical panel, this is going to be that wire there. So this is what's carrying the most electricity into the building. All right, then below that we have 1/0 gauge, and this is 150 amps. This is also going to be used for service entrance and feeder wire. And I'm not going to read through all of these, but as you can see, the gauge is going to be getting lower, or the thickness is going to be getting lower, and also the amount of wires bundled inside of the cabling is getting lower as the number associated with the gauge goes up. Okay, so as we get up here to 14, you can see we're getting to a really thin wire, and here it's just a single wire. Typically with especially residential construction, you'll be using a lot of 12 gauge and 14 gauge wire. That's kind of the most common. You might also use some 10 gauge wire here and there, but most applications will use either 12 gauge or 14 gauge. All right, so if you look at this image here, this is an example of a 14 gauge wire. This is an example of a 12 gauge wire. Whenever you see a wire that has a yellow sheathing, that'll indicate usually that it's a 12 gauge wire. If it has a white sheathing, that's usually going to be a 14 gauge wire. There are also other colors too, like orange and black, and usually the color is used to indicate the gauge of wire just by looking at it. And if you look here, you can see these numbers. So you can see that we have the 14, okay, like I said, and the 12. But then this number here, so you can see this one's a 14-2 and this one's a 14-3. That number there is indicating the number of wires inside of the cable, not including the ground wire. All right, so you can see this one here is a 2. So we have 2 wires. We have our one hot and our one neutral. Okay, this one here is a 14-3. So we have our 2 hot wires, the black and the red, and then we have our one neutral wire there. So those are our 3 wires. Same with these as well. We have our 2 wires there, and then we have our 3 wires here. The only difference between them is the gauge. All right. I wanted to touch on vintage electrical systems. Now, I don't think they mentioned this within the book or the reading, but I felt it was like a good idea to add it in here and just mention it, because if you're going to be doing renovation type work on historical structures, this is something that you will usually run into, all right? Especially stuff from like the late 1800s, early 1900s. So my house, for example, it has some of this vintage wiring in it, and it was something that I had to work around whenever we were doing renovations. So during renovations, it's common to run into vintage electrical systems. One of the most common vintage electrical system types is knob and tube wiring. Knob and tube systems consist of individual cloth insulated wires that are attached to structural framing members with ceramic knobs. All right. Wires are run through ceramic tubes at joist penetrations. These systems are ungrounded and can be dangerous. All right. So if we look at this picture here, what we're seeing is a series of individual wires. Okay. We're not going to be dealing with the cables like I showed you on the previous slides, where we have multiple wires in one bundle and one single cable. Here we have the individual wires. Okay, and one of them is going to be hot and one of them is going to be neutral, and they are separate. Anywhere where they're going to be penetrating a joist like this, so you can see these 3 holes here, they're going to run through these little tubes here. So these tubes are made of ceramic, and then for areas where they have to make bends, okay, they will be attached to the structure of the building with these little knobs. Okay, so these knobs have like a little divot or a groove in them that the wire sits into, and it holds them in place. Now these are used in a lot of, like I said, historical houses from the early 1900s, late 1800s. They're in my house. And a lot of houses today still use them. I mean, it's not still being installed, but a lot of these old houses that haven't had their wiring updated are still running on them. Now, they tend to be ungrounded, and we're going to talk a little bit more about ungrounded and what that means later on. But you know, that can cause them to be dangerous in a lot of cases. They're not ideal, but they're not the worst thing in the world. I feel like there's a misconception about knob and tube, that people think as soon as you get into a house that has knob and tube wiring, it all has to be ripped out and replaced. Ideally, it should be if it fits into like a project budget. You want to get it updated if you can, because these the insulation around these, so they're wrapped in a cloth sort of material, that'll tend to disintegrate over time, and that can cause the wires to become brittle, and that can lead to accidents like fires and stuff. So definitely you would ideally want to get them replaced if you can. But sometimes it's okay if it's there. I mean, my house, we definitely have some outlets that still run on knob and tube. Most of the house has been updated, so a lot of the circuits are fully modern and they're running on Romix wiring, like I showed you previously. But there are some runs still that are incorporating this old wiring. Okay, so it's just something that you're going to have to deal with if you're doing old renovation type work. Now this diagram here is kind of just giving you an overall sort of picture of what a knob and tube system is going to be look like installed in an old house. So you can see here are those tubes. All right, there's a tube, and then that's basically what that is right there. And then anywhere this is going to be passing through your joist, you're going to have these these are the knobs. Anywhere where you have these running through the joist, you'll have these tubes that they're passing through. And then anywhere where you have a splice, that is a wire coming off of an existing wire, okay, so it's branching off, they're going to have the joints of those soldered together, and then they're going to be wrapped with this cloth tape around it. All right. And something that you're going to see probably with a lot of older houses, if you do work in them, is sort of these areas where people who probably didn't know what they were doing will splice in new wiring to exist, or they'll try to incorporate modern wiring into the old system by splicing it into the knob and tube wiring and just using electrical tape to tie the two together. So that's what you're seeing here. And that's sort of like a nightmare for a home inspector. That's a big no-no, and that's something that they're going to flag because that's a bad thing to do. My house definitely had some of that. It's just common to see, throughout the years as people are doing renovation projects. Maybe they didn't want to pay for an electrician, or they wanted to cut corners and do it the easy way. So instead of redoing the entire thing, they'll just tie the new stuff into the old stuff and just electrical tape it together. And that is not the code standard way to do things, because that could lead to accidents. So if you ever see that, remember that is probably bad, and it should probably be corrected. All right. Okay, so grounding. I mentioned the term grounding here on the past few slides. So why is grounding important? Okay, so here what we are seeing is an ungrounded circuit, like the knob and tube, like I just said, that's an ungrounded system. And what that means is it doesn't have a route back to, or it doesn't have a route back to something that's connected to the ground. So the purpose of grounding things is for safety. So let's say you had, like this example here, there's a guy with the electric drill. He's got it plugged in. He's standing in a conductor like water, okay? If there was an electrical short, or if some kind of electrical accident were to occur, the electrical current is going to want to use your body as the conductor, and it's going to send that current through you. And it's always trying to find the ground. So an electrical current is always trying to find its way down to the ground, okay? So you can see here, the hot wire accidentally contacts the metal case of the drill. So then when it touches that metal case of the drill, it's then sending that current through the person's body down to the ground. It's using the person as a conductor, and that's going to electrocute them, okay? So that's bad, obviously. Now, if we have a grounded system, we have that ground wire in there, and the purpose of the ground wire is to redirect that dangerous electrical current back to the system and down to the ground, okay? So in this case, if the same thing were to happen, the ground wire is going to be attracting that dangerous electrical energy, and it's going to be redistributing it back through the system along this wire here back to the panel, and then that panel is going to be tied to your main water line. All right, so this pipe here, this is an example of the main water line that's running through the house. Usually that's going to be made of like copper or some kind of metal, okay? But that's going to be, that wire is going to be tied to it, and that is naturally going to discharge it to the earth. All right, so basically the ground wires are there to prevent these accidents from happening, prevent people from being electrocuted, because they are the thing that attracts the electrical energy instead of your body, okay? All right, so here on this slide, we have 120 and 240 VAC. The purpose of this slide is basically to illustrate that our electrical systems in buildings have two different levels of, or standard levels of voltages that things inside the building run on. All right, so for example, a light fixture or an outlet that's going to be running on 120 volts of electricity. A toaster, that's going to be running on 120 volts of electricity. Anything small like that, it's going to be 120 volts. Now, if we have something like a range, okay, or like a washer and dryer, those will need to pull more electricity to run, okay? 120 volts isn't going to cut it. They're going to need to run on 240 volts. Okay, so we have built into our electrical systems in our houses and in our commercial buildings different voltage levels that we can tap into for specific needs. Okay, so just be familiar with regular everyday things like lights and outlets. They're running on 120 volts. Bigger things like individual appliances, those are going to need to pull more energy. 240 volts are what those are going to run on. All right. So now the electrical panel. So the electrical panel is it's the main area where the electrical service is coming from the outside. Okay, so from the wires that are running on the poles outside into our house. So right on the inside of the house, we have our cable here. This is our main service cable that's coming from the outside inside. Then it's running to our electrical panel right here. All right. So you've probably had to deal with an electrical panel if maybe a circuit breaker trips. Maybe you were running two hair dryers at once or something, or you're pulling a lot of energy and you had one of these breakers trip and you had to run down the basement and you had to figure out which one it was and flip it back on. Okay, that's what our main panel is. So the main panel, it brings in the electrical from the outside, and then it basically subdivides all the electricity coming in into a series of circuits, okay, that are going to be distributed out toward the rest of the house to serve different purposes, okay? Within our panel here, you can see we have our series of breakers. So the breakers are individual switches or poles, if you see this term right here. So that right here, double pole for this one. This is your main power breaker. And if you were to flip this would switch off all the power in the house at one time. That's being run then to these individual breakers. So these individual breakers are tied to the individual circuits that are running through the house. And so if you were to flip one of these off, it might, turn off only the lights upstairs or only the lights in the kitchen, something like that. And these will trip, meaning they will automatically shut themselves off if they detect too much or if they detect an overload in the circuit. So if too much electricity is being pulled at once along the circuit, these are going to sense that and they're going to say, nope, that's dangerous, and they're automatically going to flip themselves off and prevent an accident from occurring, okay? These two wires right here, usually there's a bunch of different wires running off of this. Each wire is going to represent an individual circuit that's running out to the house, and the hot wires, being the black wires here, and the ground wires are going to be tying in to these sides here. So, well, the neutral wires are. These are what are known as the neutral buses. So when electricity is coming back in after being distributed, it's going to be coming through the white neutral wires, and they're going to be tying into these neutral buses here. The black wires, these are our hot wires, if you remember, and those are going to be tied to the individual circuit breakers. Okay. Then our ground wires, being the plain bare metal wires, those will also be tied onto these neutral buses. And like I said, if there was some sort of an accident that were going to occur where somebody's going to be electrocuted or something like that, the grounding mechanism is going to carry that dangerous voltage back through the wire down here into this bus. It's going to run along here to this jumper cable at the bottom. That's going to find its way through this ground wire here, downward, and this then is going to be connected to your main water line, okay, for safety reasons. You may also have what's known as a sub panel, and if you follow this cable right here, okay, that's going to take us to a sub panel. So basically a sub panel is just another version of the main breaker panel, it's just a smaller version, and this may service a particular like appliance that you have inside of your house. So for example, on my breaker panel, I have this same setup where I have this larger gauge wire coming out here, and it's running to my sub panel. And then my sub panel is going to be distributing electricity for like my washer, dryer, or something like that. So this is like a dedicated panel that's only servicing my washing machine and my dryer. Okay. This just further elaborates on what I was kind of just discussing with the distribution. So to explain this in a more clear way, electricity is distributed throughout a building using branch circuits. Electrical systems have a tree-like structure. Okay, so the main electrical panel takes all the electricity coming into the building and is going to split it into branching paths or circuits. Circuits are used to provide electrical service to different areas of a building. And sometimes a circuit is a dedicated circuit. So this means that a circuit is dedicated to a specific function. So like I said previously, for example, a dedicated circuit could be a circuit that only provides electricity to a single appliance, such as a range or a washing machine. All right, so if you look at the example here, this is just a schematic of what I just showed you in more detail in the previous slides. But we have our main power coming in from the street. We have our main electrical panel here. This is then being divided out to sub-panels. Okay, so here's our sub-panel. Then our sub-panel is further distributing that out to individual circuits. You may also have individual circuits coming out of the main panel itself. That's usually what you're going to see in a typical house, okay, a residential project. You might just have one individual sub-panel, but then the regular circuits, so these branch circuits you're seeing here, will just come off the main panel. So you might just have this one sub-panel and then a bunch of individual circuits tied to the main panel itself. All right, and then as these branch outward, they're going to service different functions. So you can see this one here is going to a bunch of different outlets and lights within the house. This one's going to multiple appliances. So if you have appliances that don't draw a uniquely large amount of energy, but they still need their own circuit, you might have 3 or more appliances tied to their own circuit. Then if you have something that just needs a ton of energy, this is where you have a dedicated circuit. Okay, so you just have one circuit coming through here and then coming out of the sub panel going to only that appliance just because it needs that much power being drawn. Okay. All right, junction boxes. So these are going to be boxes that contain electrical intersections. They allow a circuit to branch off to service different areas. So these are kind of similar to that sub panel that we were looking at here, except they don't have breakers and things like that tied to them. They're basically just either a metal or a plastic box that houses these intersections where, you know, the circuit comes in and then it needs to branch off and go 2 different directions. Okay. Electrical codes require junction boxes to be accessible. This means they cannot be buried behind a material like drywall. So if you have a like down a basement, usually you will see these exposed just attached to the joists. Okay, they're allowed to be behind like acoustic ceiling tile because you can access them by just popping the ceiling tiles off. But if you were to build like a gypsum ceiling over top of these or embed them into a wall, that'd be a big no-no, and that would get flagged on an inspection if they saw it. They can be made of metal or plastic. If they're metal, they must be grounded to the electrical wiring. Okay, so this picture that I put in here, this is actually a really bad example of like a junction box. Okay, so whoever did this was definitely an amateur. The way that this is done, it just looks very amateur-like, but it's definitely against code what was being done here. Okay, so first of all, the wiring is not done very well. There's not enough slack in this wiring, but that's a little bit nitpicky. The main point I'm trying to make here is this is not grounded. Okay, so if you look at this example that they have down here, what you're seeing is a wire coming in from the left and then another wire leaving from the right. When these wires intersect with each other, you can see that the ground wires are coming off and then they are being tied together with these wire nuts. Okay, so ground wire here, ground wire here. They're being joined with these wire nuts. At this intersection, you can see a third cable coming off of the ground wires, and that is tied to this green screw, which is screwed directly into the metal housing of this junction box. And the purpose of that is to tie the grounding system to the metal junction box for safety reasons. If you don't do that, it can be a hazard. Like I was saying with the electrocution example, the reason that we do that with these metal boxes is because they're conductive and they have to be a part of the grounding system. So if this was done poorly, like you're seeing here, how this is usually done is there is a metal faceplate over top of this when it's not being accessed. So when you're all done wiring this up, you're going to screw a metal faceplate over this. All right. Let's say one of these hot wires was exposed and was touching that metal plate. That is going to cause a hazard for somebody if they were to then go in and work on this metal box later on. If you're going to touch that and that hot wire was touching the metal but it was not grounded to the box, it would shock you. Okay, and that's really dangerous. So the purpose of this green wire, this ground wire tied to this green screw is to tie the metal box into that grounding system so that even if a hot wire was exposed and it was touching that metal surface on that junction box, you wouldn't feel a thing because the electricity would be tied to this ground wire and it would just go to that green screw and it would go through this ground wire and then it would be sent through the electrical system and to the ground through the water line. Okay. Also, another thing that they did wrong here was these clamps. You have these little clamps here that screw onto the box, and then these screw down. They clamp the wire tight so that they can't move. They put them on backwards. Okay, so obviously this was not a professional doing that, but these screws would tend to be like you're seeing here, where they're on the outside of the box and not the inside. All right, so really technical stuff, really nerdy stuff, but just things you gotta be aware of. Okay, if you're doing a renovation, you look at the electrical work that was done, you see something like this, then you're gonna know, hey, the person who lived here before probably just did things on his own and probably didn't really know what he was doing. So we should get somebody to look at this because it could be a little bit sketchy. All right. Okay, so now receptacle wiring. So when I talk about receptacle, I'm talking about anything that's receiving power from the electrical system. So in this example, we're talking about an outlet. Okay, so if we're looking at a basic outlet here, on the left side, we have our terminals. Okay, these are our silver terminals. On the right side, we have our golden terminals or brass terminals. On the left side, this is where your neutral wire is going to be tied. So basically you wrap the neutral wire, you strip it so that you just have the bare copper showing. You strip the insulation off of it. Then you wrap it around this screw here at the top. Over here on the right side, you would strip the hot wire, so the black or red wire, and then you would wrap it around this brass screw here on the right side. Okay, and that is going to complete the circuit. So if you look at the example here, we have the electricity coming through the hot wire on the right side through the brass screw. It's then going through the outlet, and then you plug your thing in, and it gives you the power to whatever you want to turn on. Then the power is then going back through the white wire and is being redistributed back to the main panel. This area up here is just our mounting. So we're going to have these installed within junction boxes. So if you look down here, here is a example of a junction box like I was showing you on the last slide here. But we have ones that are shaped for these outlets, and they're going to be mounted directly on top of these junction boxes with screws. Down here you can see is the terminal for the ground wire. So our bare ground wire is going to be screwed to that, very similar to what I showed you here. Okay, and then let's see, if we're looking at a typical outlet, you're going to be seeing the two slots here at the top. The left one is going to be for the neutral wires. Okay, so that corresponds with the silver terminals, and the right one's going to be for the hot wires, and that corresponds to the brass terminals here on the right side. And the holes here at the bottom, those are going to be for grounding purposes. Okay, so if you live in an older house, or if you've ever seen an outlet that does not have these slots at the bottom like that, those little D-shaped slots, that means that that outlet does not have grounding as a part of it. So if something like an accident were to happen, that outlet would not be protecting you because there's no grounding functionality built into it. Okay, so anytime you see that, you know that that is a grounded outlet when you see that little D-shaped hole there at the bottom of the plug. Okay, so if we're wiring up these receptacles, this is what you're going to typically see. I'm not going to go crazy in depth on this because you really don't need to know how they all go together. There used to be a class that was offered in the program called Construction Technology that I guess they got rid of, but that was one of my favorite classes when I was in the program. And that was a class where you actually got to do all the wiring hands-on and see how it all goes together and works, and you get to hook all the outlets up and then complete the circuit and plug something in and see it turn on. That was a really fun class, and we got to do all of that in that course. But basically we replicated exactly what you're seeing here. So they're just a typical outlets. It's just one circuit, and they're just going to be wired up in a series, and they're going to be connected to each other. So you're going to wire one outlet, then that wiring is going to continue onward out of that junction box. It's going to go to another outlet here, and then same thing. It's just going to keep going in a series for however many outlets you need within a space. All right. Switch wiring. So this is very similar, except this is dealing with light switches and light fixtures. So you can see we have two main types of switch currents. We have a single pole switch current and a three-way switch current. There's also four-way. That gets really complicated, so I'm not really going to talk about it. But for most lights, what you're going to be seeing is this type of situation here, where you have your electrical coming in, it's going into the junction box, and then the hot wires are passing through a switch. Okay, so basically this switch is just acting as a way to break apart the hot wires that are running through a cable. Okay, and then our switch, when we toggle it off, it's going to be breaking the connection of the hot wires, and then when we toggle it on, it's going to be reconnecting the two together. And then that's going to allow our light fixture to turn on because the electricity is going to have a full current, and it's going to be making it all the way to the light. Okay, and you can see the light here is tied to its own junction box, and that junction box is going to be grounded like I showed you previously. A three-way light circuit, this is going to be a light fixture that is controlled by two individual switches. Okay, so for example, maybe at your house you have a stairwell like I do, and at the bottom of the stairwell I have a light switch that controls a light on my landing, but then at the top of the stairwell I have another light switch that controls that same light. Or maybe in your kitchen on one wall you have a light fixture that controls the kitchen lights, but then on the other side of the kitchen there's another light fixture that controls that same light fixture in the kitchen. So that is done using a three-way switch circuit, and this is an example where you would use a 4-wire cable. So in all the previous examples, those are examples of like two-wire cables. So like a 12-2 or a 14-2 wire. In this case, you would use like a 12-3 or a 14-3 wire. And here you can see they have the two hots. So there's a hot red wire and there's a hot black wire. And I'm not going to explain how all this is going together to make this work, but that's when you would incorporate three-wire cabling to accomplish something like this, where you can control one light fixture from two different locations, okay? And there's also different configurations for how you can do this. You can have the light fixture in the middle between the two switches, or you can have the light fixture at the end with two switches that come before it, and both of these switches will control that one light fixture, okay? All right, next we have GFCIs. So a GFCI is a specialized receptacle that's going to prevent electrical shocks at specific locations. Basically, the way you can think about this is a receptacle that's tied to the grounding system, obviously for safety purposes. But if you think back to the main electrical panel and how we have a series of breakers that will trip if there is an electrical overload that's running through the system, these have a breaker inside of them that will detect if there is a grounding issue. So that type of an issue is known as a ground fault. Okay, that's why this is called a GFCI. That stands for ground fault circuit interrupter. If a ground fault occurs, then the breaker is going to trip within this receptacle, and it's automatically going to cut off power to whatever is plugged into it. Okay. So in this example, this is a classic example. Actually, I guess he's using a drill. The classic example would be a hair dryer in a bathroom that you drop into like a tub of water. So if you were running a hair dryer and you drop it into the tub of water, obviously that's bad and that's going to electrocute you and it could kill you. But if you have the hair dryer plugged into a GFCI, as soon as that hair dryer hits the water, this outlet is going to detect that, and instantly, I mean, it's so quick. If you ever watch a video about how these things work, as soon as it detects that has hit the water, it's just going to snap and it's going to cut off the power and it's going to prevent you from being electrocuted, okay? So these are required by code anywhere you are near a water source. If you need electrical anywhere within, I think it's 6 feet of a water source, it has to be a GFCI by code, just for safety reasons, okay? If this was a regular outlet, then that would be a big no-no. Now, you could have a regular outlet if the system was a GFCI system. So this is a GFCI receptacle, and this is providing GFCI functionality at a specific location, but you could have an electrical system that runs through the entire house that has a ground fault circuit interrupter built into the whole system. So that means any outlet in the entire house will automatically be able to do the same thing without it being a GFCI. Basically, the breaker. Let me just go back here really quick. These breakers, you can get GFCI breakers at the main service panel, and these will do that same thing that I told you. They sense the water and they sense the ground fault occurring, and it trips at the breaker instead of tripping at the receptacle. Okay, but those are nice because the entire system is then protected. You don't have to have individual specialized GFCI outlets everywhere to accomplish that task. You basically just have it integrated into the entire electrical system, and you're going to be protected anywhere inside of the house from these ground faults from occurring. Now, another type of receptacle that you have is an arc fault circuit interrupter. So an arc fault circuit interrupter is going to detect arcing currents between two different wires. So you know how I said we have electrical cables and there's multiple wires within those cables, like a hot wire or a neutral wire or ground wire? Um, there can be cases where maybe the insulation around one wire, actually I guess the better example would be two cables that are running next to each other. So if I'm running two separate circuits and the insulation between two of those cables is worn or broken, you can actually have the current from one cable or wire jump to another cable or wire, and that is called an arc, where they're jumping between each other. And like this is saying, if you have that, it's basically the currents jumping through the air. Okay, so you should actually look this up. I don't have a video of it, but if you look up electrical arcing, you'll probably see examples of like those Tesla machines where the arcs are flying through the air. It's basically that same sort of idea where the electrical current is flying through the air and it's passing, anything that's between that electrical current, it's going to cause to either melt or like burn. This is actually what welders use when they're welding metal. They use arc currents to heat up the metal to actually weld it. So you can see how that would be dangerous because if it's melting things and it's burning things, it's a fire hazard, okay? So an arc fault circuit interrupter is going to work very similar to the ground fault circuit interrupter, except it's going to detect those arcs jumping through the air across wires, and as soon as it detects that, it's going to cut the power to prevent fires from occurring. Now, just like a GFCI, like I said, you can have this as a receptacle like you're seeing here, or you can have it integrated and built into the circuit breakers at the panel, so the entire system would then be covered from arc faults. But a reason why you might not do that is maybe it's more expensive to integrate. So if you just needed it like in a few spots, you might just get the individual receptacles for those particular locations. All right. So this is the last page. This is just going to briefly touch on reading electrical plans. Interior designers typically specify desired receptacle locations on construction plans, or they may create a dedicated power plan if the construction plan is too crowded. Okay, so you might also put it on a furniture plan. It just depends where you can fit it. You might not need a dedicated electrical plan, but you might, depending on how complicated the electrical layout is. Something that you're seeing here might be a typical sort of drawing that an interior designer might do, or this might be something done by an electrical consultant. Receptacle dimensions are usually not indicated on the plan, but they can be if the locations are critical. All right, so let's take a look at the plan that we have here and try to decipher it. This right here is our electrical plan symbols. This is usually what you will see on a electrical plan in terms of the symbols that are represented. This plan that I have here is more simplified and it's not going to have all these, but this is usually what you'll see typically. This sort of circle with the two lines running through it, that's going to represent like an outlet, okay, or just a regular old receptacle. And they can have little symbols next to them, like this one has an S, and that indicates that's tied to a light switch. This one here just means it's a regular old outlet. It's not tied to any switches or anything. But like I said, you'll have these symbols, and then they might have a tiny little symbol next to them to indicate a specific function, okay? Basically, for this example, what you need to know is an S. It sort of looks like a dollar sign, but an S is going to indicate a light switch location, and a circle with two lines through it is going to indicate an outlet. You might also have ones that indicate GFCIs or AFCIs. It just depends. But here, if you look in this room, we have 4 outlets and then we have one light fixture in the middle of the ceiling, and that light fixture is tied to a switch, which is located right here inside of this door. And these arcing lines are going to indicate the wiring connecting the fixture to the switch. So that's indicating the circuit and how these things are tied together. So this one right here would be a better example of that. So in this room, we have 3 switches on the wall when you walk in. 2 of them are tied to this fan. So I'm assuming one is going to control the fan's actual movement, turning the fan on. And then the other one's going to control the light that's attached to that fan fixture. Then this third switch here is, you can see it's tied to all these receptacles in the room. So it goes from the switch to this receptacle, then to this receptacle, then to this one, then to this one, then to this one. So these arcing lines indicate that all of these receptacles are part of the same circuit, and they're all tied to this light switch. So if this light switch is turned off, none of these outlets are going to work, and if it's turned on, they're all going to work, okay? But basically, that's all you really need to know for this. Just for this basic example, know what an outlet is, what that looks like on a plan, and know what a switch looks like on a plan, and know that these arcing lines are actually indicating these circuits that are tying the fixtures to the switches themselves. All right, so that's going to do it for this video. I know that was probably a lot to take in, pretty complicated stuff. Just know that you just have to have a basic fundamental understanding of how these things work. If you're more interested in these concepts that I've shown you, I encourage you to look into them more. I think electrical is actually really interesting, especially the more that I've done it at my own house, and just like learned by trying it and learning how everything in the house is powered, and how you can have multiple switches controlling multiple light fixtures. I just think it's really cool. So if you want to learn more about it, go ahead and look up some videos and look more into it, but you don't need to get carried away with it. All right. So that's going to be it. If you have any questions, like always, please get in touch with me and let me know how I can help.